Welcome everyone. Today's topic of this presentation is on the proposed material requirements for Category 3 members and seismic resisting systems. And it's my pleasure to introduce our two main speakers, Alistair Fussell, the former manager of SCNZ, but he's now on his own. He's the senior engineer and technical and director of Tangent Consulting, and he does a lot of work for SCNZ. Our second speaker is Mikhail Karpenko, the general manager of the Hera Welding Center, and he'll be sharing with us some really groundbreaking research in the whole welding material space that will contribute to the proposed requirements of Category 3. Next slide, Alistair. So before I hand it over to Alistair, I just want to share with you a little bit about SCNZ, Steel Construction New Zealand. We're essentially the voice of structural steel in New Zealand, and our strengths comes from our members. We have over 430 member companies representing the whole steel supply chain, from the mills, fabricators, distributors, designers, constructors, and so we've got that expertise there. But as an organization, quite a small organization, there's 4 permanent staff. On there, you've pictured Darren O'Reilly, he's our general manager, and to the right of me is Head Hamid, who mans the technical help desk. So we provide a lot of assistance to engineers. Probably engineers represent about approximately 50% of our member companies. Next slide, Alistair. So a bit about the industry. Really pleased to report that we've really seen in the last couple of decades a real increase in the use of structural steel. And certainly the performance of structural steel through the Canterbury earthquakes and the repairability of structural steel has led to quite a dramatic increase in use of steel. If you look at Christchurch commercial projects, where 80% of that is in steel. And we're really pleased as an industry that we're trying to raise the bar in terms of quality, and in terms of our fabricators, we've introduced the Steel Fabrication Certification Scheme as a marker quality. We now have over 90% of the structural steel that's produced in New Zealand and put in place is done by an SFC fabricator. So there's approximately 50 companies now throughout New Zealand. So certainly no excuse not to specify an SFC fabricator. We're also pleased to report that over 85% of the material that's supplied in New Zealand is third-party certified. So you have increased confidence in the steel that's been put in a project meets the requirements of the standard. So at this point, I'd just like to hand over to Alistair, who will be introducing the topic today and then covering various aspects of it. So thank you, Alistair.
Well, thanks for the introduction, Kevin. Welcome everybody. Hopefully we won't have any more technical glitches today. I'd like to begin by giving you a little bit of an outline of where we're going to go in the next 40 minutes or so. Firstly, by way of introduction, I want to answer the question, why are we proposing new material requirements for Category 3 members? Then we'll talk about steels for seismic application. What are some of the factors that impact the performance of steels for seismic applications? We'll then talk a little bit about the NZS 3404 material selection criteria for seismic applications. And really the heart of the presentation is the section on what we're proposing for Category 3 member material requirements. And we'll also touch on the technical basis. So why do we think these are sound solutions for or appropriate for Category 3 members? Then we'll talk a little bit about what are some of the implications of the requirements. So if we do adopt them, what will be some of the benefits and what are some of the next steps? So really the game plan for developing this draft paper is to make some changes to the NZS 3404 material selection provision. So what are some of the next steps on that journey? What we're going to talk about today is really, well, we based the presentation on a Steel Advisor article that we published recently. It's available from the SCNZ website. Hopefully most of you have had an opportunity to download the paper. I'll be giving a bit of a high-level overview of the paper and then really focusing on what we're proposing. If you want to see all the details of what's in the paper, then you'll have to go and read it. The project is a collaborative effort between excuse me, Steel Construction New Zealand, HERA, Dr. Mikhail Kapenko, and Dr. Charles Clifton from University of Auckland. As I've said before, really the game plan, or what we're hoping to achieve by developing this paper, is that it will provide a technical basis for making some changes to NZS 3404. So what's the rationale for developing these alternative provisions? It's our view that the NZS 3404 table 12.4 material selection criteria are overly onerous for category 3 member seismic demand. And as a consequence of those requirements, they unnecessarily limit the range of compliant products that can be used as category 3 members. And this has resulted in challenges in sourcing product, particularly for columns and seismic resisting systems. It's particularly challenging trying to find solutions that work for grade 350 welded sections and also cold form hollow sections. What I'd like to do now is talk briefly about some of the factors that affect the performance of steel in seismic events. The Northridge and Kobe earthquakes in the 1990s exposed the fallacy that structural steel is an inherently fracture-resistant material. There were two types of fracture modes that were observed during that earthquake. Firstly, there was brittle fracture, and if we want to understand brittle fracture, if we were to do a tensile test, if we were to pull out a test sample and put it in a tensile test machine, and if we were to plot stress versus strain, we can contrast brittle and ductile behaviour. If we had brittle type behaviour, we would get a steel, once it reached its elastic limit, we would get very little plastic deformation before the material fractured, so that's brittle fracture. In contrast, if we had ductile behaviour, we would have steels that once they reached their elastic limit, we would get transition from elastic to plastic behaviour. We would get a significant amount of plastic deformation before the material eventually failed. And so the second type of fracture mode that was observed in those earthquakes was what's called ductile overload fracture, which, as the name suggests, the behaviour was actually very ductile. What happened was, though, that the seismic demand was so high that it actually exceeded the fracture strain capacity, so we ended up somewhere out here in the steel. So what are some of the factors that contribute to the seismic performance of structural steels? Well, it's the stress strain characteristics of the steel have a bearing on its performance, and we'll touch on that in the next slide. The V-notch toughness of the steel also impacts the performance, seismic performance of the steels, and we'll talk in a bit more depth about that later. Other factors such as the presence of crack-like features in the steel can also affect the seismic performance. So we get weld defects can introduce crack-like features. You can get inclusions in steel that are rolled in during the rolling process. Also, the loading parameters have an impact on the seismic performance of steel. So the rate at which the structure is loaded has an impact on the seismic performance, and also the number of cycles of inelastic demand. Another factor that can contribute to the seismic performance of steel is the presence of triax or restraints. So if you have a very complex three-dimensional joint and the steel is essentially constrained from deforming, then it can often end up, well, it will end up behaving in a very limited ability to deform plastically. Also, the presence of pre-strain in the steel can affect its seismic performance. So if the structure's been through perhaps a previous moderate earthquake and the steel has been yielded, that will have an impact on its performance. The steel might have been pre-strained by fabrication processes. It might have been cold bent, or on site they may have had to. They might have ended up yielding some of the steel, trying to, if they had to force it to get it to erect it and get it into place. So what are some of the stress strain characteristics of steels that contribute to good seismic performance? Well, one of the key requirements for steel, and it's a direct measure of the ductility of structural steel, is the elongation percentage at fracture value, and this is derived from a tensile test. We see here some test samples that have been taken from the steel. They've been machined into essentially what looks like a dog bone shape. The idea of machining the sample down is that we force the yielding into this neck down region. There are some gauge marks that are placed on this yielding region. We measure them prior to the test. The test is then samples put into a tensile test machine, and we get this sort of behavior here for structural steels. Once we start loading them, you'll typically get elastic, recoverable deformation. We'll reach a yield point, and then we'll transition into plastic behavior where the steel will continue to deform without any additional stress. Once we've then the steel starts to strain harden, and eventually it will reach what's known as the ultimate strength, which is the highest stress. Once we reach this ultimate strength, the sample will start to neck down, and it will eventually fracture. After the test is complete, the test sample is essentially put back together again. You measure the new distance between the gauge points, L2, which includes plastic non-recoverable deformation, and the elongation percentage at failure is the new distance between the gauge lengths L2 minus the original one divided by the original length, and that gives us our elongation at fracture value. The other stress strain or other mechanical properties that contribute to the performance of the seismic performance of the steel in an indirect way is the Fy over Fu ratio. If we decrease the Fy over Fu ratio, which means that we increase the distance or the between the yield stress or strength and the ultimate strength, we actually end up increasing the plastic hinge length, and therefore the plastic rotation capacity increases. To illustrate how that works, if we look at a simple cantilever beam, we've applied a point load to it. We can see here we have some, we've loaded, there's been some plastification of the section. Here at this point My, this is where we reach the first yield point of the section, so the outer fibre of the section has now been, has reached yield. Point MP1, which is now we have full depth plastification of the section, so it's all reached the yield strength. Point MP2, this is now the steel has started to strain harden, so it's now achieved full plastification, but it's now increased its strength to MP2. So the plastic hinge length is essentially the distance between MP1 and MP2, and the bigger the distance or the bigger the gap between the tensile or the yield strength and the tensile strength, the bigger will be the gap or the plastic hinge length. If we were to have essentially a bilinear behavior of the steel where it had an elastic portion and then just a yield plateau, MP1 and MP2 would be the same, and we would actually have no length of fully, we would have a very small or plastic hinge length. All structural steels exhibit a change from ductile to brittle behavior as the temperature of the material drops. The Sharpie V-notch impact test determines the amount of energy absorbed during a notched test sample, or absorbed by a notched test sample during fracture. This is a test specimen here. They put a V-notch in it to introduce a stress concentrator into the sample. The test consists of swinging a pendulum, and what they do is they measure the amount of energy that's absorbed in fracturing the sample, and you can actually determine or develop impact transition curves for a steel by taking samples and testing it at different temperatures. The transition temperature is taken as the transition point between ductile behaviour of the steel and brittle behaviour, and it's typically defined as the point at which, or the temperature at which, if you were to test the sample, you would have 27 joules of energy absorbed at that temperature. So above that transition point, it takes quite a bit of energy to break the sample. Once you get below that transition point, you require very little energy to break the test sample. So the energy required to fracture the sample is related to the ability of the material to resist rapid crack propagation or brittle fracture. And there are correlations that you can make between the Sharpie impact energy and the fracture toughness of the material. What I'd like to do now is talk briefly about the NZS 3404 material selection criteria for seismic applications. The NZS 3404 material provisions are intended to ensure that the grade of steel chosen can meet the expected inelastic demand, and that includes suppressing brittle fracture. So what is the expected seismic demand? NZS 3404 classifies seismic resisting systems into one of four categories based on the inelastic demand. There are three ductile systems. These are category 1 systems, fully ductile, highest inelastic demand, right through to category 3, nominally ductile, which has very low inelastic demand, and then category 4 are essentially elastically responding systems. Members can also be categorized into primary or secondary members, depending on whether they are yielding elements or whether they are protected elements using capacity design. So in 3404, table 12.2.6 has a relationship between the structure category and the member category. There's also the relationship is a function of whether the member is a primary or secondary member and whether there's been capacity design. Not surprisingly, the member seismic design demand is category dependent. So to illustrate the difference in demand between the categories, I have here an I section. It's subject to flexural bending. If we're talking about a category 4 member, which is essentially an elastically responding member, if we think about the moment curvature behavior of the steel section, we'd be talking about steels that are operating in this elastic portion up to the first yield of the section. So at that point, we've now, that's essentially we have full yielding, so we have the outer fibre of the steel has reached yield. Category 3 members experience very low inelastic demand. They're subject to about 2 times a strain of about 2 times the yield stress. So for category 3 members, we're now undergoing the transition from elastic to plastic behaviour. So this is the sort of stress distribution we get for category 3 members. Category 2 members, we have a fully plastic section, and the strain demand in the section would be in the order of about 10 times the yield strain. Once we get to category 1 members, we are now seeing strain hardening, and we're getting strain demand in the order of about 24 times the yield. So if we were to think about the flexural strain ratio between category 2 and category 3 members, it's very simple maths. It's a ratio of about 10 to 2, so it's 5 to 1. And for the category 1 members, it's about 12 to 1. So the conclusion we can draw from this is that there is a significant difference in the seismic demand between category 1 and 2 members and category 3 members. In 2007, Amendment 2, there were new material selection for seismic application criteria introduced. These are found in table 12.4, and they feature ductility requirements. So there was a maximum Fy over Fu of 0.8 value. There was a minimum percentage of elongation at fracture of 25%. There's also an upper limit on the maximum yield stress on the test certificate. The reason for this is that we're trying to maintain the strength hierarchy that was assumed during the capacity design approach. So in 3404, There's some material overstrength factors which are based on material variability of historic steels. We want to make sure that the steels aren't too strong and that we invalidate the capacity design approach and end up with actually yielding our columns rather than protecting them. The table 12.4 material requirements also include an impact toughness requirement. So this was a 70 joules at 0 degrees requirement that was introduced. This was an average of 3 tests with a minimum of 50 joules at 0 degrees from a single test. There is a limit of application for that 70 joules at 0 requirement. If you look at the notes under table 12.4 in the fine print, it says that the design surface temperature must be at least 5 degrees Celsius or greater. Unfortunately, the standard doesn't say what to do if your design surface temperature is below that. For example, you're in Queenstown, it's an external structure. You could be operating at -5, could be your design service temperature. Another point to note from the table 12.4 requirements is that there is no differentiation between Category 1, Category 2 and Category 3 members. At the time when Amendment 2 was published, there were no steel grades anywhere in the world that actually complied with the requirements of Table 12.4, and so compliance with the requirements was required to be established from the data on a material test certificate. That all changed in 2009 with the introduction and the ASNZS plate and hot rolled section standards of an S0 steel grade, which complied with the Table 12.4, made life an awful lot easier for all parties sourcing steels. Prior to that, it was a bit of a Russian roulette. The distributor had to essentially provide, essentially what it came down to was the engineer had to find some steel from steel makers in the past that looked like it was going to comply. Once the steel was sourced and a material test certificate was supplied, you would be keeping your fingers crossed that they would come up and would comply with these additional requirements of Table 12.4. NZS 3404, there are also some limitations there are limitations on the use of cold form hollow sections and seismic resisting systems. They are prohibited for Category 1 members, and they are in practice prohibited for Category 2 members. Somebody needs to demonstrate that they possess adequate ductility either by testing or rational design. And so in practice, cold form hollow sections have been used as Category 3 or Category 4 members. Just as an aside, cold form hollow sections will not comply with Table 12.4, the Category 3 requirements from Amendment 7. They typically, you won't get them complying with this 0.8 requirement. The cold forming that's required to produce a hollow section will close up the gap between the FY and the FU value. The other ductility parameter that you typically won't comply with is the 25% elongation value. They are commonly used for Category 3, but engineers have to use an alternative method for demonstrating compliance with the building code. NZS 3404 Part 1 was published in 2009, just a little history lesson on the standard. At the time when 3404 Part 1 was published, the intention had been to break up NZS 3404 into 7 parts. The idea was that once all 7 parts had been published, that they would all be cited as verification documents. Unfortunately, we never got past base 1, we never got past Part 1. Part 1 addressed material selection. It included fabrication erection, durability, architecturally exposed steelwork. So it does represent the latest material requirements. They used a slightly different approach for material selection criteria. They used a conforming steel type approach. So we can see here this Table 1. As long as you chose a steel at Type 3, you chose a Type 2 or a Type 5 steel, which essentially was an L0 steel grade, either in 250 or 300 MPa yield, or a grade 350 L0 steel or equivalent. That was all you needed to do. You were not required to check any data from a material test certificate against table 12.4. And the other point to make with that, or to note, is that there was a differentiation of requirements between the category 1 and 2 member requirements and the category 3. So category 1 and 2, they essentially required they did require either a seismic grade of steel, which was a 2S grade, or an L15 steel, which was a steel type 3 or 6. Having said that there was a conforming steel type approach used for category 3 members doesn't mean that we can't infer what material selection criteria lay behind those conforming steel types. So if you go to the product standards, that for a type 2 and a type 5 steel, you can actually determine an FY or F over FU ratio maximum value for those steel types. You can calculate what the maximum grade yield strength was for the type 2, type 5 steels. You can calculate, identify what the minimum elongation at fraction value was, and what the minimum Sharpie V-notch impact energy requirement was. This is really the key part of the presentation now. What I'd like to do is give you an overview of what we're proposing for category 3 member material requirements. We've separated out these requirements into ductility and impact toughness requirements. So the ductility requirements are have been presented in tabulated form. In terms of the maximum specified grade yield strength, we've stayed with the what's currently in Amendment 2 for Category 3, which is 360 MPa. It's equivalent to essentially a grade 350 steel. The minimum elongation at fracture has been reduced from 25% to 15%, and we have a minimum FU over FY ratio value of 1.2. So the current requirements have FY over FU, so we've essentially flipped the ratio on its head. We have two requirements. One is if you're determining the FY over FU over FY from the minimum grade requirements of the product standard, that minimum ratio is 1.2. We have a bracketed value of 1.1, and that's saying if you determine the FU over FY ratio from the actual data on a test certificate, so if you go and pull off the yield and the ultimate tensile strength off a test certificate and compute that number, you can have a slightly reduced value of 1.1. There's also the impact toughness requirements. We have two approaches. One is what we call a simplified approach, and this is pretty much the same as NZS 3404 Part 1 2009, or very similar. There's a requirement for 27 joules at 0 requirement, but it is subject to some limitations. And so we have for the Type 2 and the Type 5 steels, which is the 3404 Part 1 2009 had Type 2 and Type 5 steels. There are some limitations in terms of the minimum design service temperature of 5 degrees. We also have some maximum steel thickness requirements, and there's also a requirement that the steel hasn't been subject to any fabrication or construction induced pre-strains. Now, just as an aside, if you're wondering why we actually have differentiated requirements for Type 2 steels between hot formed and cold formed sections, and also between RHS and CHS sections, is that the process of cold forming RHS, CHS sections actually reduces the maximum permitted steel thickness for a given minimum design service temperature. You'll notice that there's also a difference between the CHS maximum thickness and the RHS maximum thickness, and the reason for that is that the minimum bend radii requirements, or they're a lot tighter, the bends in the RHS sections as opposed to CHS, so the plastic strains that are introduced are much higher, and so the impact on the maximum steel thickness is much greater. The second approach in terms of impact toughness or Sharpie V-notch impact energy requirements is that if you are outside those that simplified approach, if you're outside the limitations, you might have a material that's too thick, or the design surface temperature is too low, Well, then there's a requirement to use an advanced method by Hobacher and Kopenko. Dr. Kopenko from the Hera Welding Centre will talk about this new method later in the presentation. We have produced some NZS 3404 draft provisions that we would like to put to the Standards Committee. They have been included in the appendices of the Steel Advisor article that we have published. There are two options that we have in our provisions that we propose for establishing compliance with the ductility requirements. We have followed a conforming steel type approach, which is what the NZS 3404 Part 1 2009 adopted. So we have a list of steel types that are conforming steel types. You will note that we have some exclusions for Type 2 and Type 5 steels. This is for cold form hollow sections to AS/NZS 1163 SHS and RHS sections. The reason that we have excluded them from the conforming steel type is that if you go to the product standards for 1163 product standard for SHS and RHS sections, the minimum elongation at fracture value is only 12%, which is lower than the 15%. If you want to use an SHS or RHS section, that's not a problem. There's an alternative path that you can follow. You can also demonstrate compliance with the ductility requirements by getting a test certificate and comparing them against the requirements that we're proposing. So there is a separate pathway for such elements or such product types. So what is the technical basis? So I'd like to just touch on five reasons or five, I guess, arguments for use of why we think these are sound material requirements or fit for purpose. And the first justification is that we based it on NZS 3404, Part 1 2009. So as we've said before, this really represents the latest requirements in terms of NZS 3404, even though, as I said, it was subsequently never cited. It went through a full standards committee process. What we have done is that we have inferred mechanical properties from the conforming steel types and used that as a basis for the values that we have proposed for ductility. You can see here we included this in our paper. We essentially went through the steel Type 2, Type 5 steels from NZS 3404 Part 1 2009, and for the various grades we noted the yield values, the ultimate tensile minimum values. We determined what the FU over FY ratio was for all of these grades. We noted the minimum elongation at fracture values and also the minimum Sharpie value. If you look at the ductility requirements, and here I've tabulated them just to compare them. This is the maximum specified grade, reference grade. If you go through the list of all the conforming steel grades, 365 MPa was the maximum. This was for a Japanese steel grade, an SEM 520B or 490YB was 365. We're proposing 360. If you look at the minimum elongation at fracture values from the conforming steel types, you'll notice that for the RHS and the SHS sections, it was as low as 12%. The value that I've listed here or noted in brackets essentially is saying if you look at the circular hollow sections and if you look at all the other various plate and section standards, the lowest value that you'll find is 15%, and we've gone for 15%. If you look at the minimum FU over FY ratio, it's 1.23, and it varies between 1.23 and about 1.6-ish, and we've settled on 1.2. Minimum of 27 joules for the conforming steel types, and we have in our proposal that the steels must have a minimum of 27 joules. So our method's slightly more nuanced. What we're saying is that 27 joules at 0 degrees will often apply, but there may be some applications such as steels that are very thick or steels that are operating at a very low design service temperature where that 27 joules at 0 may be inadequate, and steels with a higher minimum Sharpie impact value might be required. Second justification is that the seismic demand warrants relaxation of the requirements. So as we previously talked about, if you compare the category 3 member demand, if you're thinking of a flexural member, and you compare them to a category 1 and a category 2 member, the ratio was 12 to 1 for category 1 to 3 and 5 to 1 for category 2 and 3 members. So what we're saying is the seismic demand warrants some relaxation, having a differentiation of requirements. And this is consistent with the work of other researchers, so you'll have to take my word for it. If you want to find out more about the work of Kuwamura and Hobacher and Kopenko, I suggest that you read the paper. They suggested requirements that are based on the seismic demand. If you think about the remainder of the NZS 3404 seismic provisions, there's also differentiation in terms of requirements between the various categories. If we think about section geometry requirements, we have requirements for category 1 members, category 2 members, category 3 members, category 4 members. If you think about the requirements in terms of connection design, the requirements vary for the different categories. If you think about if you're doing your capacity design and you're thinking about your overstrength factors, they are dependent on the category type, and also if you think about the NZS 3404 material or revisions, material provisions for seismic applications prior to Amendment 2, they differentiated between Category 1, Category 2 and Category 3 members, and post Amendment 2, thinking of the NZS 3404 Part 1 2009, there was differentiation of material requirements. The third justification is that we are utilising a state-of-the-art material selection to avoid brittle fracture methodology, and I'm going to hand you over now to Dr. Mikhail Kopenko, who's the Hera Welding Centre General Manager. He was co-author of the paper that we have used as the basis for what we're proposing.
Good day, everyone, and thanks for the introduction, Alistair and Kevin, and also thanks for raising expectations by calling this groundbreaking research. So in this case, it would be more appropriate to talk about adoption of the best international practice with some modifications. So in this part of the presentation, we will talk about material selection requirements that were published in actually in 2 papers. The first paper was published last year, and it was done under the scientific guidance of Professor Hobacher. Some of you know Professor Hobacher. He's a German expert on fatigue design and brittle fracture. And the co-authors for this paper were Dr. Stephen Hicks, Professor Brian Uy, University of Sydney, Patrick Schneider. He was master's student at Hera. He was actually doing some of that research for half a year, and myself. And the second paper we published in this year on this in IAW at International Institute of Welding. We also going to summarize results in the third paper, which will be peer-reviewed paper again. So we have some confidence the results are sound because they're peer-reviewed by friction mechanics experts, overseas experts as well. Now, the recommendations are based on modified Eurocode approach, Eurocode Part 1-10 methodology. They cover seismic and non-seismic applications. Non-seismic requirements include a range of steels, AS and ZS, EN, Japanese steels, and API steels. Seismic recommendations are limited to New Zealand, Australian, and New Zealand steels only, but they can be extended to include other steels. Selection also includes cold forming, so the hollow sections are included, but we also consider the effect of cold forming or strain hardening in the corners or in the base material of the hollow sections. We base those requirements on the known impact toughness properties of the steel from the product standards, so they are not applicable to steels without defined notch toughness. Next slide, Alistair. Right, why do we need new material selection requirements? Because there are some limitations in NZS 344 material selection procedure. Some of the limitations are NZS 344 table 12.4. It limits design service temperature for seismic applications to greater or equal of 5C. So lower temperatures, theoretically, S0 steels cannot be used. The minimum design service temperature for non-seismic applications is limited to -40. It appears to be quite low, but if you need to correct temperature because of the strain hardening, then the temperature is actually higher. And for thicker plates, the requirements are quite limiting. The requirements are not including overseas steels like Japanese and European steels. They're not applicable theoretically to those steels. And they may not be fully applicable to AS and ZS steels manufactured overseas because they are based on the test data from steel manufactured in Australia in 1960s and 70s. So there may be some limitations we don't understand. They don't account for strain hardening in hollow sections. They don't account for stress utilization, you know, how much of service load the structure receives. They don't account for any fabrication-related defects like undetected cracks, and they do not differentiate between materials of different yield strength, for example, 250 MPa or 300 MPa. Next slide, please. Right. These issues can be addressed by applying approach of the Eurocode. Eurocode 3, also EN 1993 Part 1, Part 10. We call it Eurocode 3 for the simplicity. The Eurocode 3 is based on so-called SYNTEP procedure. And this procedure includes elements of AS6 defect assessment procedure. So it's quite complex procedure. AS6, it was first developed in 1976 in the UK, and it was designed mainly for the applications in the nuclear, pressure, and piping industry. It includes the concept of so-called failure assessment diagram, FAD. And it has a major influence on related design standards. The most famous one is probably BS 1719 fracture mechanics standard, and also on SYNTEP procedure itself. So the SYNTEP procedure was developed in Europe in order to align requirements related to the assessment of steel structures in European Union. The project involved cooperation of some 17 organizations from 9 countries, and it was completed in 1999. So it was the basis for the Eurocode. Next slide, please, Arista. Right. The Eurocode 3 Part 1 Part 10 provides a table. This is a part of the table on your right side. The table includes so-called admissible plate thickness for European steels, right? It is not applicable for other steels, applicable for European steels only. And some of the parameters considered in this table are tensile and notch toughness values of the steel, properties of the steel, lowest air temperature for that application, utilization rate. It means the actual service load as a percentage of yield strength of the steel. It can be 0.75, 0.5, or 0.25 FY. The strain rate effect, for example, by accidental impact loading. The effect of cold forming can be considered. And additional safety factor can also be considered as a temperature shift. Next slide, please. However, the Eurocode 3 has also some limitations for New Zealand applications. Most notable one, it is applicable to steels manufactured in European Union, or let's say under the European standards like EN 10025, and so on. It does not include recommendations for steel subject to seismic actions. It can be applied, but it is a little bit weak on that. It is too conservative for cold-formed hollow sections, so it leads to some conservative results. And there are some new recommendations that are helping to enhance it or make it less conservative. And the minimum temperature included in the table is limited to -50. And we experience some limitations with that -50. It needs to be extended, because if you introduce temperature shift due to seismic, this actual temperature in the table needs to be lower to allow for the shift. Next slide, please. What has been done? We looked at the Eurocode, and I have to mention Professor Hobacher, who was scientific brain behind it. And the main modification to the Eurocode approach was the introduction of 3 verification models identified as VM1, 2, and 3. Those models are applicable for seismic applications, for seismic actions. Verification model 1 is the lower seismic demand. Let's say it includes residual and loadings and service loadings up to the yield point of material. Verification mod 2 includes a minimum strain of 1%. Let's say the steel goes into yielding at this stage, and the load of 1.35 times yield point. So basically, in the model 2, we can see the overstrength of the steel to account for any material's variability. So this is an overstrength factor. And the verification mod 3 considers major plastic deformation in the steel of 10%, right? In terms of relationship between verification models and seismic member categories, verification model 1 is recommended for member category 4, a verification model 2 for category 3, and category 1 or 2 should be dealt with using verification model 3. We also can consider a temperature shift, and we actually included it in the paper, temperature shift due to seismic strain rates. So if you know your seismic strain rates, the temperature can be shifted to account for those rates. But we don't recommend any shift unless you really need to do it, because I think the requirements are reasonably conservative without any shift of the temperature. Next slide, please. Right, what are the key features of this methodology? And the further difference between the Eurocode 3 and the NZS 344 is that the Eurocode considers a real welded detail. So 344 is silent in what it is. Is it steel? Is it welded? It's not welded. But in reality, everything is welded, or most of the steel is welded. So Eurocode represents a real case. And this real case is represented by so-called reference detail. The reference detail is, in this case, selected is non-load bearing attachment. You can see on the right side, non-load bearing attachment. The reason for selecting this detail is because the stress concentration factor of the detail accurately represents a range of standard structural details. For example, like a column to end plate connection. The stress concentration at the weld core is very much similar to this detail. So this detail is used in the modeling. And this detail also represents a fatigue detail category of 56. So if you look at the back of the standard, like 5100 part 6 bridge design or 344, you have details, structural details. This is fatigue detail category 56. Now, in this detail, we assume existence of a crack at the end of the weld, right? Of a little crack. Next slide, Alistair. So the reason for this crack is we don't want any crack, but the crack is a real possibility in any welded structures. And we have to assume that crack gets undetected by NDT, right? The size of undetected crack is on your sort of right corner. The size of that crack is a function of the plate thickness. And if we do cross comparison between the size of the crack A0, is so-called initial crack A0, we need to make sure it is actually detectable using NDTs. Yeah, this is not, we can include larger crack if we need to, but this is kind of crack sizes we are confident can be detected. Now, this crack will grow. So the cycles of 500,000 fatigue cycles at 56 megapascal stress range, and this nominal stress range measured in the plate is applied to this crack. So the crack will propagate. The reason for propagating this crack, we need to get more closer to reality, and we say this crack is undetectable, but structure is loaded. It may have been loaded due to seismic event, or it may have been loaded due to high cycle fatigue, and we missed crack propagation period. So the crack propagation is considered by 500,000 cycles applying to this plate, and the crack will grow to the final size. AF is identified as AF. So we know this crack, and this crack is being used for modeling, and the results are applicable to fatigue loaded structures like bridges. It equally can apply to seismically loaded structures, and it will not be high cycle fatigue crack, but crack is representative of low cycle fatigue damage in the case of seismic. Next slide. This is Scott Base, New Zealand Antarctica Scott Base, aerial photo of the Scott Base. And apparently we developed this methodology exactly for this application. So there will be redevelopment happening at the Scott Base, or it is actually happening. And the question was, what kind of steel can be used? You know, the conditions are quite tough. The temperatures can go down to -60, wind and seismic. We first look at the possibility of the development of those requirements in 2017. So we developed the first draft on commercial basis for Antarctica, New Zealand in 2017. We realized that a 344 standard cannot be used because it goes down to -40. Eurocode cannot be used because it is limited to -50. So we extended requirements, or extended the tables to -120 C. And this extension allowed us to apply temperature shift, so we can account for seismic events, we can account for strain hardening, and we can account for other conditions. Right, so the recommendations are summarized in the current paper referenced in this presentation, and also in the background papers. I will be happy to share it with you. That brings us to the end of my part of the presentation. Now it's back to you, Alistair.
Thanks, Mikhail. So in terms of the work of Hobacker and Kopenko, our intention is that this methodology, we're proposing that it would be placed in the appendices of NZS 3404. Now you might be thinking to yourself, given that there are some limitations and anomalies in the current material selection provisions, why don't we include this up front? The reason that we're proposing not to do that is that these material selection provisions are actually embedded in some of the other ASNZS standards. It includes the welding standard 1554 part 1, and also the composite bridge standard 5100 part 6. What we are proposing to do is to introduce some workarounds into the NZS 3404 material selection requirements that address some of these limitations and anomalies. So what that actually looks like is we will place some limitations on the applicability of the material selection provision. So we will identify areas of non-conservatism in the selection requirements, or if there are some limitations in the requirements, we will place some limitations. And essentially what will happen is that if designers have a situation application that's outside the scope of the material selection provisions that are in the front of the standard, then they will have to make reference to the methodology of Hobacker and Kopenko that will be at the back of the standard. That's for seismic applications. So say you had design surface temperatures that were lower than 5 degrees Celsius, or you had non-seismic provisions and you were outside the range of applicability. What we also intend to do is within the steel type relationship is to introduce some product type subcategories, and as we mentioned before, the effective cold forming hollow sections impacts on the material selection requirements, and currently the category 2 and category 5 sections which deal with which lump cold form sections in with hot form sections don't differentiate between those between requirements for those types of sections. The fourth justification we have for what we're proposing is that the ductility requirements will meet the key NZS 3404 plastic design material provision. So if you look at the inelastic demand for the plastic hinges and plastically designed members, they would be pretty similar to a category 2 member. So the demand ratio between category 2 and category 3 members was about 5:1. We do recognise though that there's a different type of loading. Plastic designs more monotonic loading, whereas it's cyclic loading for an earthquake, but we think it's a reasonable comparison to make. If you put side by side the plastic design requirements for ductility and compare them to what we're proposing, they're pretty much identical. In the plastic design requirements, there's a minimum yield length, plateau length requirement. It's not a very practical one. Nobody ever supplies a test certificate with yield length. What's actually more relevant is the minimum elongation at fracture value, and we've included requirements there for that. If you compare the minimum elongation at fracture requirements for plastically designed members, it's 15%. So it's, we're proposing something that's absolutely identical. If you look at the minimum FU over FY value, 1.2, we're following suit with that. There's a maximum specified grade reference yield strength of 350 MPa. We're proposing 360. So if you look at it, for all intents and purposes, it's pretty identical. The fifth justification is that it's similar to international practice. We're saying it would meet or exceed US, Canadian, European material provisions for all categories of ductile seismic resisting system. And there are some Japanese, only some of the Japanese material requirements for high seismic demand welded structures would be more onerous. You're going to have to take my word for it today that we're correct in saying this. We have addressed this in some length in our paper, so if you want to go into the appendices, if you've got a bit of time on your hand, you want to do a bit of light reading, feel free to go and have a look in the back of our paper to have a look at these requirements of other standards. So what would be some of the implications if we adopted what we're proposing for category 3 member requirements? Well, I think there are two key benefits that will arise from adopting them. One is that we will simplify sourcing requirements, because what we will do is we will align the seismic material requirements to a range of non-seismic steel grades. So there will be no requirement to come along and look at a test certificate and then compare them to additional and often higher, more onerous requirements and check them against the test certificate. As I said before, it's a bit like playing Russian roulette. You're hoping that the steel you order, you order it and you get the test certificates later and you hope that it complies. Well, we're going to eliminate that problem. We will also open up a greater range of compliant steels. Even though I mentioned before that there is now a seismic grade of steel, there still is only limited supply of seismic grade steels. There are very few steel mills in the world that make it. It is limited to grade 300 plate and hot rolled sections. And of the hot rolled sections, it will be UBs and UC sections. You won't get angles, you won't get PFC sections and seismic grade. You won't find any hollow sections that comply, and you won't source S0 grade 350 plate for welded sections. So, as I said, if we adopt these requirements, we should open up a lot more options for compliant steels for category 3 members. So what are the next steps? Well, as I mentioned at the outset, our goal in preparing this paper was to make some changes to the NZS 3404 material selection requirements for category 3. So you could say we've undertaken step 1, which is really to prepare a draft paper which provides the technical basis for the changes. What we're currently undertaking at the moment is a stakeholder consultation process. So we'd love it if you could download a copy of that paper, find some time in the next month or so, and we'd love to get some feedback. So we're inviting feedback by Friday, 20th of November. And then what we're proposing is to submit the provisions and in the paper to the NZS 3404 Standards Committee for consideration. The good news is that after about 12 or 13 years, the NZS 3404 Standards Committee has been reconvened, which is good news. So that it's a very it's very timely. So once again, welcome your feedback. Well, that's it from me. I'll now hand you over to my colleague, Kevin Cowie. He's just going to talk to you briefly about a couple of training opportunities for engineers.
Thank you, Alistair. Just before I do that, just to mention, we're going to have a question and answer session. So if you've had any questions through this presentation, now's the time to jot it down while I just cover a couple of engineering training items that we're doing at SCNZ. So next slide. Thanks, Alistair. So the one that we like to announce is, and we've been promoting, is a steel frame construction monitoring course, quality assurance and inspection for engineers. So this is a joint SCNZ and HERA initiative. It's an in-person event, so it's a live event with the intention is to have a lot of interaction. It's 1.5 days. It's going to be focused on the whole steel construction process. So you'll get a good appreciation on all the material requirements, welding aspects, how to undertake visual inspections, how to liaise with the welding inspector and know what questions to ask and understand what information they're providing you. It'll cover things such as erection and coatings and durability. So the registrations are open by on either the SCNZ or HERA website, so please go there, please register. There are only limited spaces available, and it's first in, first served. Next slide. Thanks, Alistair. And the other engineering presentation that we'll be doing is in the new year in February. We'll be putting on another technical webinar. Haven't quite confirmed the topic, but keep a lookout on the SCNZ website or join the and log into the Facebook and LinkedIn sites. We are planning to do in-house technical presentations as well through the months of February and March. We're just about just developing presentations for that, so we'll be covering some new material in terms of recent technical publications that SCNZ has been involved with. We'll give you an update on the standards work. I'm the chair on the revision to 3404, so we'll touch on what's going on in there. We'll cover also the updates to 5131 standard and other relevant standards to the steel industry. So that brings us to the end. So if you want to click to the next slide, if you got any questions, I'll just take a look. Right. Okay, so we've got only limited questions here. So there's just some concern that we hadn't got sound at the end there. Not sure what happened there. In terms of getting updates to steel publications, they're made available in our steel newsletter, Steel Features, which gets published every quarter. Here's another question. Will you be providing the steel construction observation course elsewhere in New Zealand? Certainly our plan is in future years we will take it around the country. This year it's going to be in Auckland and for the sort of Auckland market, but we are looking to take it to the South Island next year. Any other questions? Is there a way to ensure any amendments, changes to 3404 are recognized implemented by MB and the building code. Yeah, there's certainly a process there. Once an amendment to a standard has been made, it still needs to go up to MB to make a change in the verification document. And I understand that happens once or twice a year. So we make recommendations to MB to change it. And there's a process to follow. It's not a guaranteed outcome. The MB has to make it, make the changes and then put it out for public comment. Any other questions there? See if I can. Do you anticipate proposed Category 3 steel material changes will lead to increased import of structural steel for use in buildings? Alistair, if you want to answer that question, please.
I'm only assuming that when you say imported structural steels, you're meaning fabricated product, because most of the structural steels that are used in New Zealand projects that are supplied by New Zealand fabricators would be imported. So in theory, I guess it could do. I mean, we have to date in the steel type relationships that we will introduce into NZS 3404, we will still focus on the current standards of EN, JIS, AS, NZS steel. So I guess if somebody else had some other steels in mind, they would probably have to do an alternative solution of doing an equivalence steel type exercise on it.
Okay, thank you, Alistair. Another question here is, do you recommend engineers specifying a QA specialist be appointed as a construction reviewer, i.e. Veritas, SG, I guess that's ESGS, etc.? Maybe Alistair or Mikhail, do you want to comment on that?
Well, I'd probably just say that's probably a little bit off topic in terms of the material requirements. Look, I think if you're dealing with a certified fabricator, I'm not sure that you need a QA, an independent QA inspector for everything. We certainly recommend in the information we've published that certainly you get independent, non-destructive examination inspectors, ultrasonics to do it, but most of the other stuff would be done in-house. Certainly if you're dealing with a high-risk project, it's offshore or it's a non-certified fabricator, by all means, I think certainly getting some independent party who's responsible for ensuring the quality of the work, there's certainly some merit in that.
Okay, thank you, Alistair. What is it? Here's another one. Again, some people are having trouble hearing it. We'll see if we can send out a recording for those who are not able to hear on that. And I think that brings us to the end of the questions. So thanks, Alistair and Mikhail.